So my name's Casey. I work at a company called Netflix. How to describe what they do? So Netflix is a subscription business. So it's kind of like a library. So like a library, you get a subscription, you take your card, and you can like get out whatever book you want when you want. You can read books out of order. You're not confronted by advertisements, that sort of thing. So it's similar to a library, well, except we hire people to act out the stories. So it's like a library. So basically Netflix's value prop is that we save you from the burden of reading. But like a library, it's very popular. So it's so popular that Netflix traffic, download traffic, accounts for over 30% of the bits on the internet right now. Which by our calculation is a lot. And most of that data is coming out of the data plane. We have the world's largest CDN by far. Most of that data is coming out of the CDN. But you know, we're functional programmers, many of us here, so philosophically we're Hobbesian. We understand that state makes us civilized, but we want to keep it as small and far away from us as possible. So let's not talk about the data plane. Instead, we'll talk entirely about the control plane, which runs in AWS in 3 regions, US West, US East, and EU West. And the control plane is a microservice. Microservices mean a lot of different things to different people, different companies. So I'm going to explain what a microservice is from Netflix's point of view, and then we can draw analogies to Erlang and other systems. So here I have a diagram to scale of Netflix's microservice architecture. We have 3. For simplicity's sake, I just renamed them A through G. But an example of a microservice might be contains just information about customers, or another microservice might afford sign-up functionality or have data about movies or things like that. And we support thousands of devices. So we've never really deprecated a device, going back to like Blu-ray players from like 2007. So it's big. So a request comes in from a device, and in this case it's hitting service D, which might be our reverse proxy. And of course in a microservice, one service isn't going to be able to have all the context to respond to that request. So service D will reach out to service C and F to grab pieces of information like, oh, let me find out about this particular customer or this particular movie that they're looking at. And C will reach out to A, and F will reach out to B and G for additional information. And A will reach out to B, which G also reaches out to, and F reaches out to E. So you can see very quickly we get this, like the color isn't important, but this like green spaghetti of message passing between the different microservices. And once they've all responded to each other or timed out, the requests collate, and we return, or the responses collate rather, and we emit a response back to the device. Except I lied, we don't have 7, we actually have several hundred. Here are a few of the top ones in our streaming path. And in this visualization, you can see the circles are microservices. Here's traffic coming in from the internet and hitting our reverse proxy, and then kind of propagating through our microsystem architecture. So it's a little bit more complicated than those 7. But the problem remains that we have all of that complicated communication and message passing between them. Now, in former life, I was a consultant engineer and architect. And so I was often brought in to fix engineering problems. And what I would typically see is that engineering teams, just generalizing across the industry, new projects, long existing projects, teams will tend to optimize for one of 3 things: the performance of the application, its availability, or its fault tolerance. I can get into the difference between availability and fault tolerance later if anybody's interested, but I'll assume that this audience kind of understands the difference between those 2. And a more experienced team tends to be able to optimize for all 3 of these variables simultaneously. At Netflix, we explicitly had a fourth goal, feature velocity. So I'm sure you've heard, agile, lean. There's a bunch of process and management designed to improve feature velocity. But what I'm talking about here are architectural and engineering decisions that optimize for feature velocity. And so as engineers at Netflix, what we try to do is, yes, optimize for the bottom three, but also for this fourth variable, feature velocity. And that's one of the reasons why we chose a microservice architecture, because having a large product and dividing functionality up this way, we basically don't have one large engineering team at Netflix. It's easier to think of Netflix, the engineering org, as being comprised of like 100 or so smaller engineering teams of like 5 to 7 engineers each. And that way, each one of those engineering teams can deploy on their own cycle. They can, assume their own best practices for those 4 variables, which might differ between different functionality. And ultimately, that architecture allows the whole company to engineer faster. Slight tangent. Because we're here, and because I know a lot of you are interested in Elixir increasing in popularity and evangelizing for this language, I also am very interested in Erlang and Elixir gaining more market traction. So I'll point out that Rails, and I would love to see Elixir have some of the success that the Rails community had. Rails was successful because it optimized for feature velocity. Okay, the convention-based architecture of Rails allows any Rails engineer to pretty much move to any other Rails project and within a day pretty much know how to navigate the application. That was the key to Rails adoption. But you notice it didn't optimize for any of these other 3 things, which is interesting. So if we look to Elixir projects like Phoenix, yeah, we want to optimize for one of these things, but just copying Rails isn't going to do it. That's kind of already been done. We would need another breakthrough, and certainly with the Erlang VM underneath, we can optimize for things like performance, fault tolerance, and availability. But we also need another leap in feature velocity above and beyond convention-based architecture. That was a tangent, so let's get back to microservices. So that's what Netflix means by a microservice architecture. I hope it's transparent how you can analogize between that and an Erlang application or pretty much any other distributed system. There's a problem with this, which is that all of that messy spaghetti communication between the different services is too complicated for a human to hold in their head. So at Netflix, we don't have chief architects, we don't have architectural boards, we don't have principal architects, because typically that role is reserved for people who kind of know how all of the parts fit together. And we've just done away with that and said, you know what? Human can't do that, so we're not going to rely on that. So we lose the ability to interrogate a human and say, hey, if I add this new feature, is it going to work? And for them on high to say, oh, yeah, that kind of, or no, you really haven't considered this other thing over there. We don't have that, and that's OK. But it gives us less confidence in the distributed system. So let me highlight a particular problem in a distributed system, and I'll do it with a game called the beer game. Anybody here like beer, or am I barking up the wrong tree? OK, so a few of you. So the beer game has 3 players: customers who like beer, retailers who sell beer, and brewers who create beer. And typically, this game is played in MBA courses. So if you plan on getting an MBA and you take a systems thinking class, I'm ruining the class for you. Don't bother. Typically, how it's played, the class is divided up into 3 groups, corresponding to the 3 customers. And the object is to optimize for customer happiness, profit for the retailer, and profit for the brewer. And they're sent into different rooms, and they're only allowed to communicate to each other by passing slips of paper back and forth that indicate intent to purchase or goods or money exchanged. So I'm going to take you through a couple like facilitated rounds, and I'm condensing this, but just to make a point. The numbers aren't too important, but I'll put them up there in case anybody wants to follow along. So here in let's say week 0, the customer demand for this kind of beer. We need a name. We're in San Francisco, so we'll call it startup beer, but without the last U, because so just startup beer. So it's a relatively unknown kind of beer, although everyone secretly wants it. And so demand is for one case this week. The customers purchase one case, the retailer has 2 in stock, so they're left with 1. They order 1, the brewer has 8 ready for sale and is bottling 1. So we've got a system in steady state, right? Demand for 1 case, production of 1 case. We need a hero.
Quick question.
Yeah.
Are there only one retailer or one brewer, or are there multiple retailers and multiple brewers?
1 each.
Okay, they have monopolies in their sector.
Yes. We don't have to worry about competition. This is a far simpler game. Back to our hero. We'll call him Earl. We have an engineering mouse. And he just knows he's on the verge of an engineering breakthrough. And he just has to like sort out some thoughts and get this idea out, and then he knows stardom and fame will be his. But he just needs he's looking for a muse to help him work this idea out. And of course he's a musician, obviously, because he has a guitar. So like any good musician, he says, you know what? I just need to find my inspiration in the bottom of a beer mug. So he goes to the retailer with an intent to buy 3 cases of beer. He can only buy 2 because the retailer only has 2. I put a -2 there to indicate a loss of potential sales. The retailer orders 4 to stay ahead of this. So the brewer has 8. They start bottling 5 to stay ahead of that. And that weekend, Earl writes out a manifesto. And it's brilliant, right? This is going to change how we all do our jobs. He comes up with a concept called ops dev. And it's brilliant because it takes the best practices of one practice and applies them to another, and that always works, right? So the manifesto is great. We'll treat developers the way we've learned to optimize for things in operations. So we'll treat them hot swappable, and we'll shoot for engineers who aren't coming up with original ideas, because we want immutable engineering, right? So we want boring engineers who are easy to replace. If they're too original, they might give a talk at a conference, and then somebody might hire them away, and then you hire somebody new to come in and do the job, and they look at this very creative solution, and they can't figure it out. That's just bad. So again, from an operations standpoint, we want boring engineers, and that way we can just focus on their productivity. We can give them hand exercises so that they can type faster and increase their throughput. And in his TLDR, he credits Startup Beer for this brilliant idea. So he posts it #1 in Hacker News, obviously, and Twitter blows up. And so the next week, demand for Startup Beer from other people who want this inspiration skyrockets to 64. Of course, they can only purchase 5 because the retailer only had 5 in stock. So there's a missing demand there of 59. The retailer again wants to stay ahead of this, so they order 65 from the brewer, who opens up a new distillery and starts bottling 250 bottles to stay ahead of it. But then that weekend, something happens. We need an antagonist. I'll call him Joe. Writes a scathing rebuttal. And this is another Joe, just complete coincidence. Scathing rebuttal on Twitter. And I'll read it in its entirety. It's, dude, no. And the internet explodes, and Twitter falls down from all the retweets because they can't handle it, because they chose Cassandra as their backend, and Earl is crushed, his own personal stock, bottoms out, hits an all-time low. Earl chain, the Earl coin. It's just crushing for him. And the next week, the only one who wants to buy startup beer is Earl himself. So the demand is 3. He wants to drown his sorrows, essentially. He purchases the 3 easily enough. The retailer's left with 8. The brewer finally gets those 250 bottles in. And then the following week, we go back to steady state demand of 1 case per week, which, let's just jump to it, leaves us with this result. The retailer has 62 cases in stock, missed the opportunity of selling 61 cases. The brewer has 196 cases that they're never going to be able to sell, and an extra distillery. WTF are they going to do with that? Now, typically, this is obviously condensed. Usually, this process takes like a day to play out in 3 teams. But almost always, this is the result of the game, which is why professors like it, because it's predictable, or because it makes their students miserable, one of those. But I don't want to leave you miserable, so let's look at this cute picture of Earl the mouse instead. So if we assume that the point of the game isn't to make people feel bad, then what is the point? Well, the actual point, so specifically the point of this is to teach an effect in systems thinking called the Whiplash Effect, or the bullwhip effect, sorry, where a small perturbation in a small change in the input of a system creates a very large swing in the output. But more generally, all 3 teams are smart. They didn't do anything wrong. And yet we ended up with this result that is highly undesirable. And that's where there's a direct analogy to distributed systems and microservice architectures. Each one of these microservices could be provably correct, right? Or more reasonably, have like full unit tests, full integration tests, like they work. But the interaction between them exhibits a behavior that is undesirable. I can give you another example that's maybe a little more realistic than a musician mouse. Netflix has a show called House of Cards. Has anybody seen House of Cards? Oh, a lot of you, cool. Of course, I'm referring to the American version, but yeah. So so I'm glad a lot of you have seen it. That. Right there is the brilliance of Netflix. They turned something that is so boring nobody would stay up late worrying about it, presidential politics, and they actually made it dramatic. But in a former life, I had a job where I had to commute semi-regularly between Philadelphia and Washington, D.C., which is the perfect way to watch House of Cards, like on a train going into D.C., because the story mostly takes place in D.C. And I think it's in the 2nd season, there's like a rather dramatic scene that takes place in a subway. And so there I am on the train. I got my laptop set up on my lap and my coffee. And there's a scene, and I'm surprised. And I'm like, whoa. And I spill some coffee on my laptop. And so like any user, I start hitting refresh, right? I must have hit it 1,000 times. And of course, Amtrak, I think they use cell towers for signals. I'm not entirely sure. So there's a network partition. So all these requests back up in, I don't know, a queue in Chrome somewhere. I have no idea. And eventually, all of these requests go over and hit Netflix in the control plane, and the response I get back is a new page for Netflix that doesn't look familiar to me. So, what happened on the Netflix side? Well, one of these microservices might be a service that personalizes the experience for users. Right, so it has recommendations based on your viewing history that are specific to you. And another microservice might track information about the particular user. So a good idea, if you've got a microservice that tracks user behavior, is that you don't have all of the data for all of the users, because we have a lot, on one machine. Instead, you can use a consistent hash to make sure that the requests are distributed around a fleet of servers, and for any particular user, it hashes them and always sends those requests to the same service, the same node. Good idea. At Netflix, the engineers are also responsible for the operation of their own microservice. So they have rules like keep the service properly sized. So a cluster might have auto-scaling rules where if, I don't know, say CPU load goes below a level, it'll shrink, and if load goes above a level, the cluster will expand and will launch new instances of that node. And other things like fallbacks between different services. If it can't connect to a particular service, it will have a logical fallback. So if I can't find your specific recommendations, then I might just show you the most popular things that we have right now, which I don't know, like Zootopia and Luke Cage. I don't know what like normal people watch. But whatever like the most popular things are, we might just show those. Or display those as potential choices. And then other things like if I can't connect to a database, then maybe I just serve the answer from local cache. So the database being our canonical storage, that has the most up-to-date information. If I can't hit that for some reason, then whatever the last request I served, I'll just return that. So all of a sudden, this user microservice gets 1,000 requests for the same user, and they're all routed to the same machine because of the consistent hash. And each time it makes a lookup, it takes a certain amount of time with the database, so the database starts to not respond as quickly as it could. So that machine starts serving its response out of cache, right? Great fallback. Makes sense. Of course, serving something out of cache as opposed to hitting the database uses less computational power and other resources, so that server's CPU load goes down. So we have that scaling rule that wants to be cognizant of our cloud spend, and so it looks and says, oh, average CPU load has gone down. I'll terminate an instance to be right-sized. I'll pick that one because it has the lowest, so that one gets turned off. And the responsibility for those users gets distributed to the rest of the cluster. The personalization service, which was depending on a response for that, now sees it can't get a response because it's busy reorganizing those customers. So it returns this default of like Zootopia, which is like not something that I particularly am interested in watching. So because it's different, right, do what any user does. I start hitting refresh again, another 1,000 times. Partition, it comes through again, and it hits the new server that now has responsibility for me as a user. And the same thing happens. It switches to serving out of cache because it can't handle the database connection for that node, gets overwhelmed, and so the average CPU load goes down, so the server shrinks, so personalization starts returning this default thing. But there's multiple users involved on these different servers, so now a lot of users are seeing this default page that is not what they're used to. So what do? Yes. So they start hitting refresh. Now we have a user-induced retry storm, and all of the nodes in the subscriber in the user microservice flip to switching from cache, and so the cluster shrinks dramatically until there's only one node left, and then that falls over because it can't handle the load, and the entire Netflix service falls down because there was a very surprising scene for me in the subway in House of Cards while I was on the train. Now, this did not actually happen, maybe, but it illustrates the problem. And so far, you'd be entirely correct if you said, we're drowning here and you're just describing the water. So what do we do about it? So that's where chaos engineering comes in. You might be familiar with two chaos applications at Netflix if you follow our tech blog. One is called Chaos Monkey, and the other is called Chaos Kong. Actually, I don't know. Has anybody heard of either of these? Oh, a lot of you. Cool. So Chaos Monkey. Roughly, Chaos Monkey will pseudo-randomly pick an instance running in our cloud deployment and turn it off. I know, it didn't take long to write this. Feature velocity, remember? So This was actually really useful to us. As we moved from the data center to the cloud, we were faced with a new issue, which is that whereas things sometimes go down in the data center, sure, that's true, we were guaranteed that it would happen much more often at our scale in the cloud. Instances would just disappear. And with, I don't know, hundreds of engineers and without like an architect, or we just don't have a mechanism at Netflix for somebody to dictate to engineers. That's not how Netflix works. We engineer solutions bottom up. So there's nobody who can say, hey, we can't go down anymore from a server disappearing, so all of you have to do X. You all have to have, n=3 redundancy, or these fallbacks, or say there's a dozen best practices. We know what they are. There's just no mechanism for us to tell everybody what to do. So instead, the brilliance of Chaos Monkey is that it took that pain of being in the cloud and brought it to the forefront for every engineer in the course of their everyday work. So we don't just run this in production. We run it in our test environments and our staging environments, so that as you're developing your application, your service, during business hours, some of those instances are just going to blip out. They're going to go away. So in your first couple weeks, you're going to have to overcome that event. You're going to have to engineer in some redundancy or some way, some fallback to handle that. And we don't care how you do it, as long as you have that resiliency. And this was extremely effective. So in the last 4.5 years, we have not had an outage from a server disappearing because we brought that pain forward and made it part of the experience of all of the engineers on a regular basis. And now it's just part of our culture, and we don't have to worry about it. We thought, that's great at a small scale. So let's do it on a big scale. So Chaos Kong, where Chaos Monkey turns off a VM, Chaos Kong turns off a region. For whatever reason, AWS won't allow us to turn off an actual region. Yeah, something about having other customers there. So we simulate it, but we simulate it effectively enough. And we do this often enough that, again, all of our engineers have had to build their applications to be active-active and multi-region. And this also works. So this is from just a few weeks ago. One of my favorite headlines because of the metaphor. When S3 went down in US East, Netflix did not. It did not because we were able to move traffic out of that region to our other two regions. And we were able to do that because we run Chaos Kong often enough that we just know that that works. So we thought, OK, these two things are great, Chaos Monkey and Chaos Kong. They're very effective at giving us confidence in these particular failures. So how do we do chaos engineering like more and better? And at that point, so this was about 2 years ago, if I went around to the industry or even people in the company and asked them, hey, what's chaos engineering? If they had an answer, usually the answer was along the lines of, oh, that's when you break stuff in production. And that sounds cool for a LinkedIn profile, maybe, like I break stuff in production. But I'm sure all of us can imagine situations where we break stuff in production and that doesn't add any value to the business. So we needed something more than that. So we looked to formalize chaos engineering. And we did. We have like a manifesto-ish thing up at principlesofchaos.org. And the TLDR is that chaos engineering is the discipline of experimenting on a distributed system in order to build confidence in that system's capability to withstand turbulent conditions in production. So turbulent conditions in production, we all know stuff happens in production. We want to design experiments so that we can be confident that when that stuff happens, our system will be resilient. This is in contrast to testing. So I'm gonna call it classical testing. But in classical testing, you generally have some condition, you give it to a function or a system, and you assert an output. And if your system's more complex, then you can kind of view this as an amalgamation of functions. Chaos engineering is a form of experimentation, not testing. So strictly speaking, testing does not create new knowledge. It gives you a valence for a property. In a test, you're making an assertion, and usually it's binary. You find out it's either true or false. But in an experiment, you uncover new things. Interestingly enough, property-based testing lies somewhere in the middle, and I haven't completely thought out how that fits in. But certainly, experimentation, qualitatively different than testing. And so we have some advanced principles for chaos engineering and the experiments that we set up. One is that we build a hypothesis about the steady state behavior of a system. As engineers, we all have a temptation to want to know how something works. So our temptation in investigation is to validate that the model of the code matches our mental model. And in chaos engineering, we're saying that's not what we're trying to do. We want to verify that something works. We're less interested in how it works. Okay, so our hypothesis for the experiment is most powerful if it focuses on the steady state behavior of the system. Some KPI, some important business metric. For Netflix, it's easy. We know what the diurnal pattern looks like for play starts, video starts per second. So we have a KPI called SPS, starts per second, that we have up on charts and stuff that we can see. We know it goes up a little bit before 6 o'clock Eastern time, and it's a very smooth, very nicely bounded metric. So we know what our steady state behavior is. Vary real-world events. So obviously, we don't want to introduce variables that aren't effective. We want to look at things that actually happen. Hard disk going bad, servers disappearing, network partitions, high latency. It's not all failures, good things, sudden increases in traffic, things that aren't good or bad, just weird combinations of things hitting at a time, and operational effects. Experiment in production. At Netflix, this is easy because for us to build a system that replicates our production system and tests would be too costly, so we just can't do it. But we think this is valuable as a general advanced principle because in an experiment, you're going to have things affecting different systems in different ways. And if you're running chaos experiments on not your production system, then you're building confidence in not your production system, which is much less valuable. So really, chaos engineering has to take place in production. And automate experiments to run continuously. This isn't something that can effectively be done manually, so we put a lot of emphasis on automating our experimentation. So these are our advanced principles. It resonated with the community, so we ran a Chaos Community Day last year in San Francisco, this past year in Seattle. All of the usual suspects, Google, Microsoft, Yahoo, AWS, et cetera, many startups. So this concept, this formalization of chaos engineering certainly resonates. If you're interested, go there, sign up at to the Google group, or come find me. We'll have another one this year, at least one more this year. So let me illustrate the tools a little bit more. So again, say we want to test something similar to what I described earlier. We have a gateway, a reverse proxy, an API layer, and then a personalization service. What we can do is as the requests come into the gateway, we can randomly select, or pseudo-randomly select, some percent of requests to participate in an experiment. And as those requests populate, fan out through the system, in this case, I've designated one of those requests as red to indicate that it's part of the experiment. We have injection points in the client libraries between different services. And at those injection points, we can say, based on the context in the request header, whether or not we take action. So in this case, we'll allow that request to pass through, except when it tries to go from API to the personalization service, we'll cancel it. We'll add latency, or we'll time it out, or we'll return an error, or whatever. And then we'll see, hey, does that have an effect on SPS? So this is a graph of our starts per second. And our first tool, FIT, Failure Injection Toolkit, did this. The problem is we started an experiment right there where we did this to 10% of traffic. And you can kind of see something there, but you know, I don't know. Is it statistically significant? So there were a couple problems with that approach. One is that people might come across that error and hit retry, and as they come through the second time, they're not part of the experiment, so it just works. We can fix that by making that sticky so that those users are always forced into that experiment. And so we came up with a couple other things that would allow us to have a better empirical setup, a better automated experimental setup. We came up with what we call Chap, the Chaos Automation Platform. And what Chap does is it will take a service that we want to study, in this case service C, and it'll spin up two nodes identical to the rest of the service, a control and an experimental group. Here you can see they're deployed in the cloud. And we'll apply the condition or event to the experimental group, and then we'll just compare those requests as they come out of the system, at the system boundary. So it looks more like this. We can select a smaller amount, 1% of requests for the control and 1% for the experiment. And as they travel through, that injection point says, OK, most of the traffic's going to regular API. 1% is going to API control, and 1% is going to API experiment. And then as those requests propagate, the API experimental group fails out its response to personalization. Here you can see the SPS for those two groups. The colors, again, don't matter, but one of these lines is red, one is blue. Roughly, the SPS looks the same, which is great. That gives us confidence that having this failure where API cannot talk to personalization does not affect SPS. Here's another way of looking at it. On the left are the successful responses. The blue line shown in the left that you have some height to was the control group. The red line at the bottom is flat because we failed all of them, then we're successful. And on the right you have the fallback successes. So the fallback was triggered for the experimental group, which has some height here, and the blue line is flat at the bottom because the control didn't have any fallbacks. But CPU utilization was much higher for the experimental group. So that worked. And then finally, we have a chaos maturity model because we're engineers, so of course we overload acronyms. So CMM measures two axes, sophistication and adoption. Sophistication is the adherence to those advanced principles of chaos engineering, is the hypothesis about steady state, varying real-world effects, running in production. Other things like, can you automatically stop a chaos experiment if something bad is happening to those customers? Because that would be bad. And adoption. Does the leadership in your organization buy into it? Is there a self-service tool? Are teams actually using this? Adoption tends to be a little bit more straightforward to measure. And if you put these two together, then you can have a nice quadrant where when we talk to other companies, we try to help them figure out where does their chaos fall into these quadrants. So Chaos Kong and Chaos Monkey have been around for a while. They're both very sophisticated and have high adoption at Netflix. We're just starting out with Chap, although in the past quarter we've made some significant improvements to its sophistication, so now we have to work on adoption. And do I have 5 minutes left? Yep. So in the 5 minutes that I have left, I want to touch on another idea. So that's basically what I'm going to tell you about chaos engineering. I want to touch on another idea because I think this is important for distributed systems engineering. And that's intuition engineering. We just make up these new disciplines in software at Netflix. We just do it all the time. So intuition engineering, we have an application called Visceral. But when we're running a traffic failover, when we're moving all those users out of one region to another, we've got great metrics. So we can put up like 48 charts, and we can see all of the relevant things changing through time. And we can dig through those to know, oh, is it safe to move users over? Problem is, it takes long for a human to be able to dig through all those charts. So what intuition engineering does is it focuses on creating user experiences that in an instant give you a sense of the state of the system. I have an absurd metaphor for this, but it works. So anybody here ever on call? Okay, okay, cool. So some of you can relate. So imagine we made a suit and we covered it in electrodes. And the placement of the electrodes corresponds to different microservices. And if that microservice goes down, then you get zapped there. Now, when you're on call, you have the privilege of wearing the suit. Internally at Netflix, we call this affectionately the Payne Suit. And the hypothesis is that after wearing the Payne Suit for a very short period of time, you would just have a sense of the state of the system. And somebody could ask you, hey, how's Netflix doing? And you'd be like, yeah, it's pretty good. Or you wake up at 3 in the morning, your shoulder hurts, and you're like, oh, subscriber's down again. Damn it. Now, we haven't built the Payne Suit yet, but we did create a visual analog. And that is visceral. So the dots moving represent requests. The big circle in the middle is the internet. Those are our 3 regions. So these are request responses going out to the 3 regions. Blue dots are successful requests. Occasionally you see a red one, which is an error. Occasionally an orange one, which is a fallback. And in about as long as I've been talking about this, your brain has already kind of sort of figured out what normal looks like for the volume of dots, the speed, the color, the motion. And so at a glance, we can look at this and know, oh yeah, everything looks normal. And this has proved to be invaluable to us as we manage distributed systems. And I have a lot more to say about that, but that'll have to wait for a different venue. So I don't think we have any time left. I'm just an engineering manager. I don't actually do work, so these are the people who do the real work. I work at Netflix. I'll be here for most of the rest of the conference. So cool. Thanks.
Thank you.